he was talking about at the end of using TS diagrams as a way to look at endpoints and analyze how the mixing behaviors we observe differ from what it would be like under certain theories as a way to test our theory. That's kind of what we're doing for this lab. So let's get into it. So this is our buoyant plume. This is us. Here's a diagram of what this thing generally looks like. This is again what Drew was talking about. The diffusive port at the very bottom. There's a lot of fish like to hang out around it. The plume comes out in a series of ports. So each of these ports, depending on, I don't know, draw or probably pressure, would have maybe a slightly different amount of emitted properties. Yeah, and then it comes up and it's subjected to all these currents, it's subjected to buoyancy, and then it may or may not get up to the plume to get up to the surface where some, let's say, people are going to stick a CPD in it. So this is kind of the different ranges of places around an outfall. So most of what I am talking about in terms of the mixing lines really applies only in this very near field region where it has to do with what is coming out and what immediately happens to it. So if you look at the spatial scale, it's like within 10 meters of the port. So definitely finer detail than most of what we can accomplish usually with sampling. And then in the intermediate field, then there's the buoyancy effects, all of that kind of takes over, but that is still kind of considered in the near field. Then far away is the ocean. So yeah, that's the plume. There's a near field. Here's some terminology for these things. So near versus far field. In this very close region, that's kind of called the discharge mixing zone, or sometimes you might see initial mixing zone. It's important because that is an EPA definition. And inside of this mixing zone, some of the restrict regulations we have are relaxed because the whole point of this region is for it to mix. And eventually, when you're away from it, that is when a lot of the EPA regulations apply. Okay. Right, so as a result, it is very important for us to understand what the heck is going on in this region. All right, so TS diagrams. Just physics one, PO. Physical Oceanography 101 background. I'm TAing this year, so this is me practicing as well. This is a TS diagram. It is a type of state space. So it is not a physical location, but rather this diagram represents all possible configurations that you can have of the system. And then regions on this stuff in this space kind of tells you about like a whole class like of objects. Things that are here in this space act like this. So these boxes are the different water masses. I turned the bottom water, that is this one, and it's also the freshest one. It comes from like melting and lineas, off Antarctica, gets to the bottom, spreads around. Here's another important one, MPW is from the North Pacific. And then all of that has this like big, large scale global circulation currents that kind of last about, I don't know, 1,500 years. Something like that. Actually, it's sort of like my candidate. There are some water masses in the middle of the North Pacific that has not seen the air since the Byzantine Empire. I think that's really cool. Okay, cool. So yeah, state space, all possible values that we have. In our case, it's temperature and salinity, not to be confused with temperature entropy plots, which are also called TS diagrams, also relevant, and in fact can be used together. If you're like thinking about heat budgets and stuff. In this space, isopatenals are curved, and that is because the equation of state we have for density is super nonlinear and complicated and whatever. So when you put the pressure, when you put the density, they are these like lines. So right here, under the bottom water and North Atlantic deep water, similar-ish density, similar-ish. But very different in terms of properties. Yeah. Okay, another thing might be relevant to us. So this is all possible places in the ocean and some like specific regions. If you're thinking about one profile and your sensor going through a water column, what it's doing is actually moving in between all of these regions. So it moves from the surface water into whatever's on in the middle into here, the deep, which probably this will look a little bit like somewhere in the heart of bottom water and North Pacific water. So just another thing to think about as you're analyzing TS diagrams, like what does it mean? Are you plotting things that are from one moving vehicle? Are you plotting things that is from a time series? All of those things might give you a slightly different interpretation of how you would approach analyses. Questions, concerns? Great. All right, so again, what Drew already kind of introduced for us. A game you can play with these kind of space diagrams is you can say, if I have two distinct water parcels, which each occupy one place on the line. Here, the two have the exact same density, so they are very happy to come together and mix in the same place. If you bring them together, the properties of the resulting combined water mass will be like a linear combination of the properties of the initial water mass. So when you bring them together, what they should, if you take that intermediate like mixed stuff and then you put it on this line, it should sit on this initial mixing line. It should. That's it. And that leads to weird things. For example, right here, you kind of see that like it's really curved. Especially as you get to pressure waters. So this happens a lot at high latitude, where if you will have two water masses of the same density and then they mix, but the resulting water mass will actually be denser than either of the parents. And then it winds up sinking. That creates all sorts of rapid diffusion issues called cabling. If there's a more fun German name that I wish we use, it's like storm track. It's fun. I would, yeah. But we call it cabling, whatever. So this is in theory how that linear mixing should occur. But of course, turbulence and mixing and all sorts of other processes will mess with this view. All right. So now back to effluents. So this is a schematic of a TS diagram. Now we are very, very zoomed out. Notice that there's no like nets associated with either temperature or salinity. So if A now is the effluent, the water that is it's usually really fresh. It's usually a little bit warmer, but you will see that that temperature changes over time. So I have to like play around with a bunch of these. What you can do is draw a line between the two. Notice there's a break here because this is just straight and it's a forming line for a beer. And then usually, I mean, you can even see it before in our, in this one, usually TS diagrams wind up looking like a line for a single profile. So usually this line is what that TS diagram looks like. So what mixing does is these water parcels, when the two combine, they want to stay on this line, but then eventually, depending on what is happening, what kind of mixing is occurring, and all sorts of nonlinear combinations thereof, these points will kind of veer off that line in a curve, in a family of curves. So studying that curve should theoretically tell you something about the mixing that is occurring. This is some equations for that like straight line. We're going to be doing this on the computer, so it's just using terp. Anyway, cool. So here is that theory applied to some data. So here's that is actually CDOM. They were doing this near a water ocean outfall and stand-up outfall. So very comparable to our region. It's actually very common to do this, especially in the Southern California in like California and Southern California, because our continental shelf kind of like really steeply curves off, and then the actual shelf part is relatively narrow. So it's not that hard to build a pipe that goes all the way to the end of it. And as we kind of saw, it actually did a pretty good job in like making sure that stuff does not come off. Sure. That was about. Anyway, back to mixing. So here, these are the initial mixing lines, and they just look like it was coming from nowhere, because remember, the other point of this line is all mixed together. And then if you can color these points on a TS diagram by CDON in this case, you kind of see that like in general, there is a line. This is perhaps a mixing line that goes from like the bottom properties to the top, and then just normal vertical mixing. And then this is the plume stuff. Kind of imagine that perhaps like each of these points follow that curve somewhere coming off of this straight line. But this method has a lot of approximations. Like you have to know for sure what the point is at the other end. And as I said, it's not very constant, and the information is not super public. But if you do know that information, then you can kind of do the thing that Drew was showing, which is you have a straight line and you can just calculate how everything veers off from that line. Our method is a little bit more. It shouldn't work that well, but in general, there are many parts of the TS diagram that does act like a line. And that is perhaps a little surprising given everything that happens in the ocean. So as you look at your TS diagrams, see if you can identify some of these lines, and they might be telling you about like important end members that are maybe coming to cover. Okay, cool. I'm blowing through most of this because I wanted to have more time to go into the actual analysis. Okay, so this is a source. Excuse my dark mode. This is what it looks like when the water goes in. It goes through primary treatment or enhanced primary treatment. And then it comes out looking like this. So that's what water looks like when it's coming out of the port, and why we see the elevated turbidity signal. From the paper, they kind of gave a range for possible temperatures. They used 30 degrees, but when I was looking around, it's different in the winter versus the summer. And also that this initial mixing is for the most part salinity driven. And that makes sense, just the salinity values is so big, between 0 and 30 something, whereas the temperature is like similar. So that initial mixing is primarily driven by this. Which is why we care about the spice, and Grant is calculating a lot of that. Okay, cool. This is that daily cycle that I was talking about. People don't poop as much at night, I guess. And we produce a lot of wastewater in the morning, kind of a dip, and then again in the evening. So it's really like a human behavior kind of thing. Hard to predict, but just keep that in mind as we look at all of our data. Cool. Oh, and then finally, last note to end on, a temperature salinity is not the only states that matter for the things that we care about. You can have all sorts of states diagrams. Here's our boring TS. Temperature oxygen is a good one. Oxygen nitrate is one of my favorite. I think that's somewhere on here. But this is from that P17 line that I showed an example of earlier. But you can do any. This is a method. You can apply it to the world. Okay, great. So that's the static lecture part. Oh my god. Oh, am I still screen sharing? Because I want to put my super notebook on here. I think this is exit out here.
Yeah, you are still screen sharing.
Okay, great. Let me know if this is working.
That isn't showing up.
Okay. All right, let me get this set up on here first, and we'll work on it soon. Apologies, folks. Thank you for your patience. We're the only people on the Zoom.
We are, but I'm recording.
Oh, good point. That's
In
right.
the future.
All right. All right, future people, probably including me. Let's go. So I've just like coded up a very basic example. I've mentioned before that this time was not the first time I've ever gone on this browse specifically looking for this plume. So in 2022, we were cruise SP 2204. We should recognize that format from our data. And this was our ship track. This data is very poorly organized, so that was why I never quite got around to a lot of it. But what that also means is that a lot of this data has been unexamined, and I think it's interesting. So if you are interested, we can keep going. This red line here is the specific section that I pulled out for our example here. So this is what that data looks like. So here was our CCD, was moving up down water column. And then if you do like interpolate, you kind of get a cool little section plot that looks something like this. Great, but really what we care about is putting it onto a TS space. So here is that full TS line. As we see, our section is only a very, very little part of it. That's pretty common. Like if you look at the whole possibility of temperatures and salinities that water be, the entire ocean sits in a very, very little narrow triangle part of it. It's especially narrow and salinity. Anyway, so this is where we're starting with. I put down two possibilities just because I also don't know where we're starting with. This is now that I zoom in to our well, the plot that I was showing you earlier, all of the stuff I've got, kind of see like all these wiggles. And then when you really zoom into the zone of interest, there's a lot of structure here. And as we were just saying, the structures in the TS diagram perhaps tells us something about mixing and properties thereof. So let's slap our mixing lines on here. And maybe we can do some sort of like conditioning to pick out where I think our plumes are. And here are the two mixing lines that I kind of suggested when I gave the case earlier. We kind of calculate like how far it is from that. This is very imprecise, but it is powerful. So that's kind of as far as I got with this example. But also what you can do is, okay, now let's say this is our end instead. Forget what's going on at the side of the plant with this effluent. Maybe what if, now that we've identified the plume, let's say this is our end member, and then we want to see what's going on with, like maybe we found that this part is actually right next to it. Now you can play that mixing line again with those two. That's what we want. So a whole lot of options. All right, so now it's your turn. Kaylee has very kindly put together our data. We have a better. Oh, look at that! It worked. Thank you. Yeah. So this is our data. It's on the drive. In fact, this is where it is on the drive. If you are curious. Prosper. I don't know. Oh, this is one example of what our stuff looked like. You see the version? That little bell, is that it? I don't know. And then you have a lot of options where we can look at. I chose a bunch of CTD data, but it does not have to be the CTD. You can use the concerto with this. You can use the clue warning with this, but just keep in mind that the kind of data affects the way you should be interpreting what you are seeing. Yeah, all right, a lot of freedom. Okay, yeah, so just check out this directory on the drive.
Is it with your?
It's in data, ship process data, CTD Rosette.
I see.
CTD transects. I did it this way so I can specifically point it. Like that's where it is, guys. And then the concertos are also in the same place, except for instead of should process data, it's in mod process data. Everyone can just kind of pick their favorite files. If you wind up picking the same ones, maybe you can sit next to each other and discuss. Yeah, just start with start with the TS diagram. And then probably the next thing is to just color it by something you find interesting. That'll help you identify your end members. And then once you have your end members, then you can put a line between the two and look at the other points that should be along that line. See if it falls on that line. And if somebody does this with something other than temperature and salinity, let me know. I'm really curious. Assuming you're all diligently working, but if you have a question, please let me know. And I have 11. Oops, give up. This is not even a point. Yeah.
No, I think that was great. That's a.
I know for something about the.
So I will try the sense and see.
So we have until noon at around like 5 before. So you guys, hey, what are some things that you've found so far? And have gotten far. This is very much a starting place. So awesome.
Hold on, is school one the same thing as the.
Oh,
we
so-
also have- is it one of-
Those are exactly the same. It's just
Okay.
one is a,
Okay.
and it's not to a bonus tone, but I think there's someone that's supposed to abundance.
I see, okay, so I need to change.
Yeah, you don't need to change any of this. That was me when I made those CSV files. You just.
I see, okay.
Thank you. Right. Yeah. If you're on my Jupyter notebook, ignore this line. This is what I was using to like make the CSV files that's in that folder. So the.
Helen, maybe is GPS and things also you, okay, just making sure.
Yes.
Apologies. I don't know.
Does that mean that you, can't plot this one?
So I assume tour is what we wanna load in.
Yes, it's really, you just want it to load into, if you're on the Jupyter, apologies, folks. Let me fix those other stuff.
Each. Yeah. Yes, yeah, we just have to read them, but.
Okay, great. I'm gonna put, oh. Oh, that's different. Gonna update this on the. Thank you for troubleshooting.
I think it literally you just need a cell in the data. That's just like opening the NC file. That's okay.
Yeah, usually that's. This is confusing, I'm trying to easier.
Yeah. Yeah, when I was doing it, I was like, should I give all the data if people want to explore everything? Some sense for what you want it. So yeah, it's a choice. In one more variable for TSP.
Sorry.
TSP.
Yes.
Define. Oh, it's defined. I see.
Yeah, it's defined.
I think it's just defined after it leaves the B. The cell below the one where you do the mixing line to the source. Yeah, that one.
So.
And that's the background. And
Nothing fun exists. What are weird transits? No, this is me trying to plot up that transit that we were looking at. What are some things that people have been plotting? Have we all been looking? Oh, shoot. Have we all been looking at the exact same file or? Other transects. Okay. Did any of you see the plume in your transects? I don't know why I still do this. No? Hey, Kaylee, what's up? Okay. Okay. T-beam transmission. Yeah, totally. That makes sense. Beam transmission should be the inverse of turbidity, right? Yeah, less transmission, more stuff in the water. So if there are two little dips, then that's like two different places where we have very turbid water, which even if my thing would fix itself, okay, nope, we're not fixing anything. Great. But that is a feature that we have been seeing. So that's really cool that you can see it too. I'm interested, did they have their like own little space on the TS diagram? Like, you know how we saw that plume that may or may not have come from the river? It's like really fresh and also turbid, right? What's going on? Was that also part of that? Yeah, right? It should be in the TS diagram. That's cool. Thank you. Thank you for sharing. Anyone else? Oh, okay, cool. Do you guys just want to go to lunch? Is that what this is? Because that's very valid. Oh my god, yay, Kaiki! Woo! Thank you.
So these are some of the TS plots from the transects. And I'm plotting CDOM. I think it's kind of cool to see that like the plume kind of hangs out always at the same space in the TS diagram. Sometimes the like surrounding water seems to be like kind of farther away from it. Sometimes it's closer. I don't know what's going on. But yeah, I think we can clearly see the plume. This is like zooming in. There's also like a version is backscattered. This is the C dome, like, so this is the whole TS plot and the plume. No. In terms of mixing lines, I think we should define like one mixing line here, other mixing line here.
Usually I see them saying like use the stick. I was walking around with. He's gone. Thank you. So if you look at that like main plot, it looks like that has one slope. But then the place with the high CDOM, like this here, it has this kind of slope, right? But then the CDOM is always a little bit below it, and it always kind of looks like there's this other slope that is like maybe more closer to the CDOM parts. And I think that is an indication that it came from a different mixing line. So I think we can't necessarily back out the dilution because like there's so much, but the difference between the two are like, if we can see like a consistent line in just the CDOM parts, I wonder if with enough data, we can get a dilution. Because yeah, if you fit a line, the slope of that line should tell you the direction. So I think it's possible. I think, oh,
Cool.
that'd be really cool.
Anyways, this is more of a.
Wait, and I'm also sorry. So one of our weirdest sections is that deployment 3. And
Yeah, I don't know if the data is good on deployment tree.
yeah, maybe the data's not good. But in any case, if we like think about lines, there's a lot of different lines kind of sitting on top of each other. And I imagine if we go into the deployment, maybe they come from like different profiles, or maybe they're from like different depths. I don't think it's fully gibberish. And I think some parts of it look enough like the deployment score that like between the two, we might be able to back out what was going on. Because I think something else might have actually been happening.
Yeah, I think the TS data is definitely like, okay, just the follower of the CDOM, I think CDOM's messed up for this one. I don't know.
Thanks. I think that means it's also a good way to kind of recover sometimes when we're like, oh, we don't know if the CDOM comes, right? So therefore, we should be able to pinpoint something about which points should have been the elevated CDOM and maybe back out like from there. If there's a way to scale everything else. You are free to go. It is afternoon. So